Hi guys, I'm Monica. I welcome you all to my channel Aeroper. So in this video, we will be doing something new. In our previous video, we looked at conservation of mass and when it is applied to fluids, what kind of equation we get. So in this video, what we are going to do is we are going to take the Newton's second law and apply it to the moving fluid. Now, all of you might have studied Newton's three laws in your schooling days. So, one of those Newton's second law that we are going to consider over here. What is the Newton's second law? It says F is equal to ma. In the mathematical form, it can be represented as F is equal to ma, that is, force is equal to mass into acceleration. F is the force exerted on a body of mass m. A is the acceleration. Now, in general, I can also write this equation as d by dt of mv. So this is what you see here, that is d by dt of mv. The term mv over here is known as the momentum of body of mass m. If you observe the another form of Newton's second law, that is F is equal to d by dt of mv, it reminds you of the physical principle, the three physical principles that we had gone through in our previous videos, which says it is based on Newton's second law. That means force is equal to time rate of change of momentum. So this is the mathematical expression which exactly represents that physical principle. In this video, what we are going to do is take this physical principle and apply it to our moving fluid. Now, where the fluid is moving, where are we going to apply, and what we are going to do? Let us have a look. Same thing as we did in our conservation of mass, we are going to consider a small region or domain, which we call it as the control volume, and apply this physical principle to this control volume. And note that this control volume is fixed in space and the fluid is moving through it. This control volume, let us consider a small elemental area ds, which has a velocity v, and a small finite infinitesimal fluid element whose volume is given by dv, that is the differential volume, and this v is the volume of the control volume that we have considered, and s would be the area of the control volume, that is the control surface. The surface area of this control volume would be given by S. Proceeding further, applying the physical principle to this control volume that we have considered. Now, initially what we will do is we will try to obtain the expression for the left hand side of the equation, which is the force. What are the forces acting on this fluid when it is flowing through this fixed control volume? So in order to obtain the expression for the force that is acting on the fluid which is flowing through this control volume, we need to know what are the sources of force acting on this fluid. So the sources of force are body force and the surface forces. We have two sources over here. Now, what is this body force term over here? What does it include? So, in body forces, we have forces due to gravity. Then we also have electromagnetic forces or any other force which is acting at some distance in the control volume. These are the forces which would be considered inside the term body forces. Moving on to the second source, that is the surface forces. Now, in case of surface forces, we have two. One is the pressure force, and the second is that of the shear stress that is acting on the fluid when it is flowing through the control volume. Now, let us consider that this small F, the letter F is representing the net body force per unit mass that is exerted on the fluid which is flowing inside the control volume. So if I want to see what is the body force acting on that small infinitesimal volume, that is dV, if I have to write the expression for the body force acting on that, that would be given by rho F dV. So this would be the expression for the body force that is acting on the elemental volume. Now we have found out this for the elemental volume. What about the whole control volume? If I want to write the expression, the body force, expression for body force that is acting on the whole control volume, it is a very simple task. We just have to integrate it, and that gives me the body force over the whole control volume. Note here that this V is for the whole control volume, and when I say it for a small element, you get this as a small v. And while deriving, also do not forget to number your equations. Let's consider this as our equation 1, and this is our equation 2, and the body force that is acting on the whole control volume, this would be our equation 3. We are done with the first type of force, that is body forces. Now we need to obtain the expression for the second source, that is the surface forces. Now if I want to obtain the expression for that elemental, on that small elemental surface that we had considered, that is ds. Now elemental surface force due to pressure, the small elemental surface force that is acting on this elemental surface area ds is given by minus p ds. Now as you can see, I have put here as minus pds. What is the reason behind this negative sign? So this negative sign indicates that the pressure force is acting in the opposite direction of ds. That is, when you look at this control volume, this is the direction of ds which is pointing out of the control volume, which means my pressure is acting opposite to the direction of ds. That is, the pressure force is acting on the control volume due to the surroundings. If I want to write the complete pressure force that is acting on the whole control surface, that would be the integral of the above term, that is integral of minus surface integral of minus p ds. This would be our equation 4. Now, is this the only surface force that we can consider? As we had discussed that in surface forces we have pressure force and shear stress. So in case we are having a viscous flow, if it is the viscous flow that you are considering, then there are normal and shear viscous stresses that are acting on the fluid along the control surface when the fluid is flowing. So here what we will do is, let us consider the term F viscous. So let us say that this F viscous is denoting the total viscous force that is exerted on the whole control surface. So we have got all the forces that are acting on the control volume through the control surface. So the final expression, that would be my left hand side of the equation, which is denoted by F. So what would that be? The sum of body forces plus the sum of surface forces. So in terms of body forces, what we had derived, the first one, the body forces, the volume integral of rho f dv, and the negative pressure force because it is acting on the surface, and the viscous force. So this gives me the expression for the left hand side of our equation. This would be our equation 6. This was about the left hand side of the equation. Proceeding with the right hand side of the equation, which was d by dt of mv. That says the rate of change of momentum. So on the right hand side, we have the rate of change of momentum of the fluid as it sweeps through the fixed control volume. Now, this time rate of change of momentum is a sum of two terms. What are those two terms? The first term is the net flow of momentum out of the control volume across the control surface F. Let us denote this term by the letter capital G. And the second term would be the time rate of change of momentum due to unsteady fluctuations of flow properties inside the control volume. And let us denote this term by capital H. So first we proceed with the term G. Now, when the flow is entering the control volume, it has a certain momentum, and when it is leaving the control volume, it has a different momentum, and this is due to the forces that are acting on the fluid. Now, if I want to get the net flow of momentum which is going out of the control volume across the control surface S, that would be simply the outflow minus inflow of the momentum which was across the control surface, and that we have denoted by G. So we know that mass flow across the elemental area ds can be written as rho v ds. This is the mass flow which we had also seen in our conservation of mass. So if I know the expression for mass flow, then can I write the flow of momentum per second across ds as rho v ds into v? That would be my flow of momentum per second across that elemental surface ds. And the net flow of momentum out of the control volume through the surface would be the integral of the term. So that can be given as G is equals surface integral of rho v ds into v. So this would be our equation 8. Now, as you see, the term G, which is for the overall control volume, is a positive value, which means it is representing the mass flow that is going outside the control volume. Whereas if it was negative, then it would represent mass flow into the control volume. Said this integral is a combination of contributions of both outflow and inflow. That is the negative contributions. If it is an inflow, then it is a negative contribution, and if it is an outflow, then it is a positive contribution. So the positive indicates the net flow out of the momentum. Now, because this G is having a positive value, what we can say is more momentum is flowing outside of the control volume per second than the one that is entering the control volume. If G would have been negative, then we would say that more momentum is entering the control volume when compared to the one that is leaving the control volume. So this was the first term of our right hand side. Proceeding with our second term, that is H, which says the time rate of change of momentum due to unsteady fluctuations. So the momentum of the fluid inside the elemental volume, the small elemental volume that we had considered, that is dV, would be given as rho dV into V. And if it is for the whole control volume, that is the momentum contained at any instant inside the whole control volume is given by the integral of this term rho v dV. Now I have to write the time rate of change of momentum. We have got what is the momentum. Our motto is to write the time rate of change of momentum, which is the second term, and that is denoted by H. So this would be our time rate of change of momentum. note one thing, that wherever it is small v, it is for the elemental volume, and when I write d and capital V in this way, it is for the whole control volume. This would be my equation 9. So now in order to get the total time rate of change of momentum that is sweeping through the control volume, that is our right hand side term d by dt of mv, it would be g plus h, that is surface integral of rho v ds into v, and the volume integral of rho v dv. This is our equation 10. Now, all these terms that we have got right from the starting, that is the total, which is our f, our equation 6 and our equation 10. We have to apply it to the Newton's second law, which says F is equal to d by dt of mv. So when we apply it to the Newton's second law, this is the final equation that we obtain upon the substitution of all the terms. Equation that we have obtained over here after applying the Newton's second law to the movement of the fluid is known as the momentum equation, which is one of the governing equations of fluid dynamics and aerodynamics. Now this equation, as you can see, it is in a vector form, and it is the relation of aerodynamic phenomenon over a finite region, and as you can see, it is an integral form. It is not for a small specific point, as we had seen in conservation of mass. Now, what if I want to get an equation for a small confined point? As we can see here, for this particular point, I want to write a momentum equation. What is it that we need to do? Convert this integral form into the partial differential form. How do we do that? Let us have a look. So first, what we are going to do is we are going to apply the gradient theorem to the first term of the right hand side of the equation, that is to this term we are going to apply the gradient theorem. So upon application of gradient theorem, this pressure gets converted into the gradient of pressure and in terms of volume integral as well. So when I substitute this term, this would be the momentum equation. Let us say this is our equation 13 probably, and this would be 11, 12. So whenever you're deriving, keep the track of the number of equations so that it's easy to go back and look at the term when you're deriving. Now, as I said, that this equation that we have got is in the vector form, so which means I can write it for 3 different directions, right? And if we are considering Cartesian coordinates for the term velocity, that is the capital V, which is being denoted by capital V over here. So I can write in terms of Cartesian coordinates as something of this sort, that is ui cap, vj cap, and w k cap. Writing in that form, then my x component of the equations looks something of this sort, which includes all the terms, and as you can see, the u term has come, which denotes the velocity in the x direction. And as you can see, the force is written as Fx, and we have Fx viscous over here, which denotes the viscous force acting in the x direction. Proceeding further is what we do is applying the divergence theorem to the surface integral on the left hand side, that is to this. One thing to be noted over here is that this term rho v ds, it is a scalar, so it will have no components, no other components. So once we apply the divergence theorem, in our previous video we had seen the divergence theorem, and upon the application, when it is applied, it gives me the term in the form of a volume integral. So this is my volume integral as I apply the divergence theorem to the term. So upon substituting and solving, this is the final equation that we obtain. Let us see, this is our equation 16. So Fx over here denotes the proper viscous force, that is the shear stresses acting due to the viscous flow in the x direction. Now, as seen in the conservation of mass, the integrand at all points is 0. So when I say integrand at all points is 0, what happens to the above equation? So when the integrand becomes 0, we obtain the equation in this form, that is the partial differential form. Now, as I said, we can write it in three different directions. So these three equations represent the x, y, and z directions, where u, v, and w are the velocities in three different directions. Fx, Fy, and Fz denote the viscous forces in x, y, and z directions respectively. So these three equations, they are applicable to unsteady three-dimensional flows, either it be compressible or incompressible, viscous or inviscid. So these are the momentum equations in partial differential form. Now we saw that these equations are for unsteady flow. What happens if I say that my flow is steady? What would be the condition? In our previous videos, we had seen that the condition for steady flow is there is no change in any property with respect to time. Either it be any property, for example, if it's density, then it would be the change with respect to time would be 0. So if I'm considering for a steady, that is our first case, the second would be inviscid, in which my viscous forces would be absent. And then the third condition I put is that there are no body forces. So which means F viscous would be 0, and then F would be 0. So when I substitute these assumptions, what happens to the equation in the integral form and the partial differential form? So when I substitute these assumptions in the form of integral, I am left with these terms. And if it is in the partial differential form, then this is what we are left with. So this would be my equation 18, and then we have 19a, b, and c. So these three equations, after using these assumptions of steady, inviscid, and no body forces, the equations that we have obtained are known as the Euler's equations. And the partial differential form over here, with considering all the forces, that we have seen, that is 17a, b, and c. These equations are the famous Navier-Stokes equations, which is one of the building blocks of aerodynamics, fluid dynamics. So whenever we proceed or have a discussion in our journey, as we proceed with our journey in aerodynamics, so this term, Navier-Stokes equation, is the term you're going to encounter n number of times. So I suggest all of you to remember this, what Navier-Stokes equation is all about. And also in our journey further, we will be discussing the significance of this Navier-Stokes equation, that why it is so much important, and where and all it is applicable. So thank you for listening. Stay tuned.